This is the ESP Roll, a small home-built spherical robot that moves by rolling around in a ball. Perfect for entertaining your pets, exploring under furniture, or just having fun with friends. And you can build it in a weekend. You can even drive it in first person like an FPV drone, but on the ground in a rolling ball. Glides on tiles, grass, carpet, and even sand without any sensors for balancing or external wheels touching the ground. Based on an ESP32 camera, it runs 2 motors, has clever weight placement, a clean 3D printed chassis, and a transparent ornament shell. I'm Max, and in this video I'll take you through the full build process behind it, so grab your tools and let's roll. Laid out are the things we need for the project, including a lithium battery, geared motors, wire, power connectors, slide switch, buzzer, LEDs, surface mount components for controlling peripherals like motors and lights, a Xiao ESP32S3 Sense camera with its accessories, main board and ring light PCBs, metal hardware, weights, zip ties, PLA and TPU for the 3D printed parts, and the shells of a transparent plastic ornament. You're looking at around $60 worth of parts as of June 2025, excluding shipping, to build the ball bot. Find all the parts with product links to obtain them in the video description. Let's start with the PCB that ties everything together inside the ball bot. Here's how I designed it. I jumped into Flux and started by searching up all the parts, from the Xiao camera to the tiniest passive components, and placing them onto the canvas. I spent a while digging through all kinds of contradicting motor driver schematics online based on the same chip until Copilot stepped in and suggested the right way to wire it up. That really saved me a ton of time and let me follow the correct schematic confidently. I also reached out to the GitHub author of the code I'm using and asked if I could add a buzzer for low battery warnings. Once they explained how, I added the buzzer along with a voltage divider for battery monitoring and a MOSFET to drive the head and tail lights. I thought I'd get clever with a latching power circuit using a push button, but after trying a few options, I decided to keep it simple for you guys with a basic sliding switch, which wrapped up the schematic. From there, I imported a custom board outline and laid out the components as they would actually sit, with mounting holes and connector pads. After routing the power and signal traces, I turned on copper fills and opened the AI Design Review tab. It flagged a few issues and helped me fix them fast, making sure nothing got missed. With that done and some branding added, the 2-layer PCB for the robot was ready to go. If you're like me and prefer designing your own projects from scratch that use PCBs, Flux is worth checking out. It's free to start with up to 5 projects and monthly credits given to test out all the AI tools. So feel free to sign up to Flux with the link in the description. Also linked in the description along with the other project files are the schematics and Gerber files for both PCBs, which I'm providing for free. That includes a second board I designed, an LED ring light that wraps around the camera to act as a mini spotlight. Once you've downloaded the 2 PCB Gerber files, you'll need to outsource manufacturing to a service like JLC PCB, who provide affordable, reliable boards for DIY projects like this. Let me show you how easy the ordering process is. Head to their site and upload the Gerber zip files to get an instant quote for the ESP Rolls PCBs. For the specs, set both boards to 2 layers, choose how many copies you want, set the main board's thickness to 1.6 millimeters and the ring light board to 1 millimeter. Pick your favorite board color and enable remove order number to keep your PCBs clean. Leave the rest of the options as is. Now scroll down and enable the PCB stencil option only for the main board, which includes small surface mount parts like the motor driver IC. Those are tricky to solder by hand. Set the stencil size to 80 by 50 millimeters and select the top side only. Add both PCBs to your cart, making sure the main board includes the stencil, then check out. You'll be able to track the order from their fast 24-hour manufacturing through to shipping. Mine arrived in just a few days. JLC PCB manufactures 1 to 8 layer boards starting at just $2, and their quality standards are top tier. So to get your boards made, click the link in the description and sign up to get $70 in new user coupons from JLC PCB. Once you have the PCBs, let's move on to assembling them, starting with applying solder paste to each of the pads of the main board using its PCB stencil. We'll surround the board with some perf boards of the same height and tape them down. Aligning the stencil over the board will tape that down, apply a blob of solder paste, and spread it right over. We'll carefully remove it, revealing the coated pads. Let's do the same for the LED ring light PCB, only without a stencil, as each pad is large enough to cover with the solder paste syringe alone. Now let's pick and place the main board's surface mount components. Here goes the resistors for the tail and headlights, the battery measuring voltage dividers resistors, power LED resistor, motor driver pull-up resistor, MOSFET pull-down resistor, capacitors for the motor driver, a red power LED, LED MOSFET, and the dual motor driver IC. If you have troubles finding this exact motor driver chip, consider salvaging it, reusing the driver and its surrounding components from its modular form. For the ring light PCB, the only SMD components are the current limiting resistors for each LED. Now we can place each board onto a hot plate, alternatively a hot air gun, and watch the components melt into place while correcting those that get misaligned. If the chip's pins get shorted with excess solder, simply use a soldering iron to clean them up. Next up, let's install the brain of the whole ball bot, the Xiao ESP32S3 Sense from Seeed Studio. This tiny dev board is the camera-equipped version of the same microcontroller I used in my ESP Fly project. I designed the project's PCB so it slots right on top using the castellated holes. It sits flat like this, and with a bit of soldering paste across the sides, it locks into place and connects to the circuit. I chose this board because it packs a lot into a tiny footprint. Built-in Wi-Fi for low latency phone control, a 2-megapixel camera for FPV video, a microphone, and even a micro SD card slot for recording videos you can play back later. It also runs directly off a 1-cell battery and handles charging. No extra circuitry needed. Once it's soldered, we'll flip the board over and wire the battery pads on the bottom of the Xiao to the PCB, which holds the battery connector. This board is compact, low power, and saves space, perfect when everything needs to fit inside a sphere. You'll find Seeed Studio's Xiao ESP32S3 Sense linked in the description among product links of the other supplies you'll need. Now let's install the through-hole components, starting with the SPDT slide switch for controlling power to the board, a 5-volt active buzzer for motion detection and low battery alerts, 3mm white and red LEDs for the bot's head and tail lights, bent 90 degrees so they point outward when in place. We'll also insert a JST battery connector and solder all of these components, followed by trimming the protruding pins flush. Then we can hook up the motors to the bottom of the board with some 28 gauge wire. I've added markings to show the correct polarity and which side each motor belongs to. Speaking of which, you mustn't forget to bridge these 2 pads beside the motor driver, or else the chip will not run. This pulls high a sleep pin, and also the voltage divider pads to enable voltage monitoring. With the Xiao came an included heatsink, which will stick onto the bottom of the microcontroller to keep it cool, using the space I created for it in the design of the main PCB. Without it, the camera would get as hot as 70 or more degrees Celsius, but with the heatsink, it runs at 50 to no more than 60 degrees. Another part that comes included with the ESP32 was this antenna, which will modify by desoldering the flex PCB part of it, stripping a section of the coax cable enamel, revealing the stranded wire shielding, which will trim off, exposing the insulated bit of wire that we'll keep as the antenna. From my experience, this actually improves the signal. We'll clip on our customized antenna to the Xiao's UFL connector and clip back on the camera module. For you, now would be a good time to load the firmware, as this will allow you to make sure the whole circuit works before putting everything into the casing. However, I'll cover the code part later in the video. Speaking of the casing and all the structural parts that the electronics go into, let me take you through how I designed this ball bot in the CAD software called Autodesk Fusion. I started by making a virtual sphere like the ornament shell the ESP roll sits in, took measurements of each and every single component and modeled them in Fusion, did the maths to end up with how each one should sit, which is what helped me create the PCB shape. Then I was able to model around it, creating the enclosure and supporting parts like the weight holder and caster wheel arms. From there, I designed the wheels of the correct diameter and added some finer details such as the branding, symbols, mounts for certain components, and color. To 3D print or tweak your own ball bot to your liking, the STLs, modifiable files, and all the details are listed on Cults 3D. Check out the link in the description. Next, let's print the structural parts and wheels of the ESP roll. I'll go with dark gray PLA filament for the first batch. I'm using the Elegoo Neptune 4 Plus 3D printer, which I run for all my current projects. Once it's heated and loaded with filament, I'll start the first print. It's got a huge build volume, wider than a dinner plate, and hits 500 millimeters per second speeds without losing print quality, which saves me time without sacrificing results. Just 2 hours later, the first batch is done. Now let's swap over to TPU, the rubbery filament for the tires, which gives the ball bot better grip. I'll feed it in and kick off the next batch. This printer handles a range of materials: PLA, PETG, TPU, ABS, ASA, and even nylon, so it covers everything needed for my recent and future builds. If the Neptune 4 Plus looks like a fit for your projects, there's a link to it in the description. With all the PLA and TPU parts 3D printed out, it's time to remove supports and clean them up. To mount the board and weights, we'll need to install 5 of these M3 threaded inserts, 4 into the body shell and 1 into the battery/weight holder, like so. Before installing motors, we must secure the weight holder onto the bottom of the main body with the shortest possible M3 screw. Then we need to add strips of electrical tape as insulation on the motors to prevent them from shorting the pins on the bottom of the board. Only then can we shove them in and route the wires in such way so that the main board can be pushed into place. Afterward, we'll secure each motor with a couple of M1.6 screws, 5mm in length. Now let's assemble the caster wheel arms. Each gets a tiny 3D printed TPU wheel inserted with a short piece of 1.5mm steel wire as the pin that it rotates around. We'll secure each arm with a couple of 6mm long M3 screws into the body of the bot. The wheels should rotate smoothly and work to support the bot from wobbling too much inside the ball. Let's go ahead, push in, and solder 12 of these 3mm LEDs into the ring light PCB with its SMD resistors already in place. We'll trim away the excess pins and hook it up to the bot via a couple of wires to power it, connecting to the external LED pads designed for the ring light. Then we can superglue it in place and insert the camera, making it protrude through the hole. To come up with the wheels, we'll mount the TPU tires onto the PLA wheel hubs with a perfect fit, and then simply push them onto the motor shafts without any glue, leaving room for the robot's height adjustment within the ball later. Attaching the battery is as simple as lacing through a couple of small zip ties around it through the weight holder's holes and also adding the weight of your choice. I'm using a 1/4 ounce or 7-gram weight to start with. Then we can plug the battery into the connector up here. Now we'll use something like a toothpick and a marker to color in the DBoss text and symbols around the ball bot. For the transparent plastic ball this robot will sit in, we'll use one of these fillable clear ornaments. Unpacking them, each ball comes in 2 halves you simply put together with a tight fit to form the ball. But one thing is in the way that has to go, and that is the tabs that form the loop for hanging the ornament. Now the ball can roll without running into some knob, so when you go to use it, you switch it on and close the shells around it, completing the spherical robot. So far, you're watching the video tutorial of this project, but if you want a written version of this entire build, complete with photos, diagrams, and step-by-step instructions, you'll find the project blog for the ESP Roll on Elector Labs. Check the link in the description. Alright, let's program the robot. We'll be using a code called ESP32Cam MJPEG2SD from the GitHub author S60SC. It's a motion capture web application for ESP32 cameras that I've used for DIY security cameras and RC cars in the past. Its primary feature is image-based motion detection, which is how it triggers video recording. Accepts a whole host of different sensors and peripherals, such as a motor driver used with the remote control capability for vehicles we'll be using primarily, and is even machine learning capable for detecting specific objects if you train it. So you'll want to head to this repository linked below and download the zip file for the code and unzip it in its location. Then rename the folder, removing -master from its name. Open the .ino file, loading the Arduino IDE. You should see all the surrounding files appear as well in their own tabs. Go to the app globals header file, and in the board selection section, comment out all boards except for the Xiao ESP32S3 that we're using. Leave it uncommented. Scroll down a bit more and set include peripherals to true, and do the same for include MCPWM, which enables the driving of motors. Now go to the peripherals file in the section for battery monitoring under the battery task function and type out what I just pasted here under line 309 to ensure the buzzer beeps when the battery's voltage drops below a set minimum threshold. That is all you need to worry about changing in the code. We can then connect up the ESP roll to our computer and check we have the correct board info set under tools. Ensuring Xiao ESP32S3 is selected as the board, on boot should be enabled, select default with SPIFs as the partition scheme, enable PSRAM, and select the COM port the ESP is connected to. Then we can hit upload and wait a couple of minutes for the code to be flashed to the ESP roll. Then we'll need to take a micro SD card, plug it in, and copy over this data folder to the card, which is for storing your configuration parameters. The card will also be used to save video recordings. Okay, we'll want to eject the micro SD and push it into the ESP32 and then power it all up. We can connect to its access point Wi-Fi network through a device and go to a web browser to type in its IP address, which should be the same for you, 192.168.4.1. Then we should get a panel that looks something like this. Pressing Start Stream will run the real-time video feed, but to complete the setup, we'll go to the Edit Config tab. Then under Peripherals, let's scroll down a bit and enable Remote Control. Set our desired duration 1 second for the buzzer to beep when motion's detected. Set the pin it's connected to, which is 6. Enable it, then head down to voltage check interval and set it to 1 minute. Set the low voltage warning to go at 3.5 volts. Set pin 5 as the analog to digital pin that monitors voltage, and enable this feature. Now we can scroll up and enter the RC config tab. Set the pin used for lights to 43, your desired speed thresholds, and set the pins for both motors to 1, 4, 2, and 3 in this order. Scrolling up, we need to hit save and reboot to implement the changes. This will restart the ESP32, requiring us to reconnect to its access point. Sometimes it'll do it automatically. After a refresh, all should be set to start using the application. Tapping the game controller icon makes the remote control sliders and lights button appear. You get forward, reverse, and left-right controls with proportionate speed. If you hit one of these buttons, you set the video stream to full screen for a better view while controlling the bot. If you tap on the bulb icon down here, you get basic on-off control of the lights. But if you want proportionate brightness control, head to RC config and erase the lamp pin number, and instead enter it in the Peripherals tab next to where it says Pin Used for Lamp, and save the changes. Open the camera controls sidebar and play around with the last slider for the lamp's proportionate brightness control. When the BallBot, something or someone moves in front of the camera, it'll start recording video, triggered by the detected motion, and keep recording until there's no more movement detected. And recording can also be controlled manually. If you go to the motion detect and recording sidebar, you can turn the motion detection feature on or off. In playback and file transfers, you can select any clip that was recorded to the memory card and play it back here in the browser, or even download them. Alternatively, you can connect the card to your computer and play the videos or save them there. Apart from the BallBot beeping when it starts recording, when the battery goes low, it'll make a continuous beep, indicating that you need to charge it, and it won't shut up until you turn it off or restart it. Also, when charging, make sure the bot is switched on to connect the battery. When fully charged, it should read 4 to 4.2 volts in the web panel. In the camera controls sidebar, you can adjust the resolution at which the camera streams and records. Set it to CIF and you get 30 FPS with low resolution. Set it to UXGA and you get a hacky 5 FPS but at a higher resolution. But set it to SVGA and you get something in between, which I find to work best. Now, if you want to skip adding all of these parameters as I've shown in both the web app and code, simply use the same data folder containing my configurations and code that I modified linked in the description below in the ESP-Roll project files folder. And for more guidance on setting up your ESP32 camera with the motion capture application, watch this video I have linked in the description below that dives even deeper. With the ESP-Roll finally set up, we can now play around with it. Controlling it is fairly straightforward. Move the right slider to steer it, it'll simply turn in its place. Move the left slider to make it roll forward or reverse. And if you combine the two controls, you can make it roll while turning. But if you experience it wobbling back and forth or worse, flipping around like I had it, you need to give it some heavier weights. Around your home, think of any heavy metal parts of the right size. The heavier, the better. I went with a steel cover originally used to house a neodymium magnet, attached it under the battery, slapped on a couple of magnets, and added these long cap nuts. This weighs 50 grams alone and 65 with the battery and other weight, while the BallBot itself weighs just about the same. So this was before, and this is after adding the weight. Again, the more weight you add without scraping the inside of the ball, the better it'll perform. The spherical robot is all set up, ready to roll, and just before we give it a spin, ever wondered where to build up the skills for projects like this? If you're keen to dive deeper into ESP32, Arduino, or electronics, Electra Magazine is packed with expert tips, hands-on projects, and solid knowledge to level up your projects. Right now, for a limited time, you can get a 1-year Electra Green digital subscription for half price. Find the link in the description. Alright, now let's see it in action. Let's see how it rolls on grass. Okay, what about the beach? If the ball is sealed well enough, could the ESP-Roll go on water? But but I don't recommend you do this as water can easily slip into the ball like it did despite the tape, unless you use silicone to give it a watertight seal. How about we make it go through an obstacle course? Now let's get a first-person view from the ESP roll. Alright, now you've seen what the ESP roll can do. If I've inspired you to build it, go check out the links below. I've dropped all of what you need to get started, including the parts list, diagrams, code, 3D files, PCB Gerbers. So start by acquiring the parts, taking it a step at a time, and before you know it, you'll have your own little rolling robot cruising around your home. As always, if you can imagine it, you can make it. Till next time.
What do you think? Huh? What do you think?